Awesome. Yeah, thank you very much. Yeah, good morning. Or morning for me here in Austin, Texas. Good afternoon, evening, wherever you are. Yeah, so I will be talking for the next 45, 50 minutes about Dask. The talk is going to serve three purposes, really. One, just to be kind of an introduction, a high-level overview of Dask. Two, to introduce some new libraries that we've been working on, collaborating with PyHEP folks to plug Dask a little bit more into PyHEP packages. And three, as a little bit of an appetizer for a couple of presentations that will be following, that will follow up this tutorial. So yeah, we'll go ahead and get started. Kind of the first little bit of the notebook is just almost like a slide here. So Dask is a pure Python library for parallel computing and distributed computing, really to scale up the PyData ecosystem. So I know Dask has been mentioned at least a couple of times here during PyHEP, but kind of starting from square one here, just really starting as if everyone has no knowledge of Dask. We have Dask broken into two main components. There's the collections library or libraries, depending on how you like to see it. Sometimes this is referred to as Dask core. And listed here, there's the Dask array library, the Dask bag library, Dask data frame, and Dask delayed. So these all serve a purpose of partitioning or chunking existing Python workflows such that they can be distributed. So in Dask array's case, this is partitioning or chunking NumPy, and Dask bag, this is just regular Python objects, anything that can be iterated on in Python. Dask data frame, this maps to pandas workflows, and Dask delayed is meant for parallelizing any kind of any Python workflow that you can dream up that perhaps doesn't fit into one of the PyData libraries. So Dask itself is a PyData library, but really what it's doing is it is just scaling up the existing PyData libraries. Secondary to the collections libraries are the execution engines. So what Dask does is it builds task graphs, and we'll talk a little bit more about that. And once the task graph has been created with one of the collection APIs, then it needs to be executed, and it gets executed by a scheduler. So there are a number of schedulers. When you just spin up Dask for the first time on a laptop, you get the threaded scheduler usually. So this is just some, Dask will take advantage of all the threads on your machine. But then there's also the dedicated distributed project, which is sometimes called Dask distributed. And this is for scaling up on perhaps a cluster that is available to you, some HPC system, or perhaps the cloud. So those are the two main components of Dask. There's the library to create task graphs, the collections libraries, and then there's the execution engines. So this graphic here really kind of shows that, illustrates this in a single picture where there is an API, the collections API for creating task graphs that get passed to a scheduler for execution. So that is the very high-level view of the Dask project, the Dask ecosystem. Really, it's not just a single project. And so, yeah, I mentioned here there are a number of other projects in the ecosystem leveraging both of these components, and we'll be talking a little bit more about that later too. So I'll start off with the first example here using Dask delayed. So Dask delayed is the collection library that really allows you to turn any Python workflow into a task graph. So I'm defining a function here called just increment the argument. So it takes in x, it returns x plus 1. And then I'm just turning this function into a delayed version of the same function. So if I do this and I pass in 7 to inc, I'm not actually going to get 8. I'm going to get a delayed object. So I can assign this now to a variable called 8. And to actually get a result, you have to say compute. You're telling Dask, compute this thing. So I get the answer 8. This is one of the things about Dask that I remember when I first started using it. It took me a second, not a second, it took me a little while to wrap my brain around it. And that is that Dask objects are just some staged thing. It's lazily evaluated. So when you're doing things with the Dask API, until you actually call compute, you're just staging up something to happen. Everything is lazy. So taking this a step further, we can chain together delayed calls. So here I'm using the decorator syntax. So now I'm having my increment function and combining this with an add function. So I can say increment 1 and increment 2, and then add those together. So of course, 1 plus 1, 2, 2 plus 1, 3. This will be 5. Didn't execute that cell. There we go. So now one of the powerful things about delayed is you can pass delayed objects into other functions that are that have been decorated as a delayed, as a Dask delayed object. So one of the really cool things about Dask, and especially using Dask in like a Jupyter notebook, for example, like this workflow here, is there are a lot of diagnostics and tools to actually see what's going on. But before we look at that, I'm going to bear with me while I spend just a quick second on a little bit lower level than what is typical, what would be typical diagnostics, and that is some details about exactly how Dask represents the task graph. So I'm going to take this task graph of adding 2 and 3, and I'm going to call the Dask property and convert that to a dictionary. The Dask property on a Dask collection is the task graph. And so the way that Dask actually stores this information, the task graph, is in just a plain Python dictionary. So what Dask is doing is it's creating something kind of Lispy. Every task has a label and then some function, some lazy function call represented by a tuple. And the way that Dask can chain these together is that the label assigned to a task can be passed into a later task. So starting with the 2 increment functions, I have my increment of 2. So the first element in the tuple is a callable. In this case, it's my function increment. And then the later arguments are the arguments to be passed to that function. Same thing with incrementing 1. But then you'll notice that the increment steps are then the arguments in the add step. So this is a very, very low level view of Dask, but it's to me, I think it's a very useful thing to have in mind as to exactly how Dask is executing is accomplishing the task of building a task graph and then executing it. So when Dask goes to compute this, the final thing it wants to do is the add function, but it will see when it comes into the add function that it needs to compute the increment steps first. So then it'll walk down the graph and it'll compute these steps in order to accomplish the complete task graph. Like I said, this is a very low level view. It's not the easiest thing to parse. There's a much better way of inspection, and Dask has a visualized method on the collections so that one can actually look at a picture of the graph. So we see obviously that there are 2 increment calls going into an add, and then the circles are function calls and the squares are data resulting from those steps in the task graph. So that's the most verbose example I'll give today, but it really is a core example of it really surrounds the full Dask landscape and what's getting accomplished. Okay, so now moving on to something that is a little bit more targeted to perhaps a workflow that folks here at PyHEP might be interested in. So here in the second example, we'll still use delayed here one more time. We'll look at something that is loading a file, doing something with the contents that you've loaded, and then histogramming that calculation. So we'll leverage Dask, and then we'll compare this to not using Dask. So I've got a few imports here just from the ecosystem here, uproot, awkward, hist, and I'm also just borrowing a file from scikit-hep's test data. So I just have one root file that I'm just copying 4 times for and kind of the example purposes here. So the 3 steps, really 4, but the last 2 are very similar. We're going to read in some tree with uproot, and I added a little time sleep 1 second here to fake making the file larger. We're going to do some calculation by passing in the tree, and that calculation is just going to be taking the absolute value of the differences in energies and the particles in this file. Then we're going to histogram that value by taking in some data and defining a bin, the binning. And then finally, because we are doing this over multiple files, we're going to aggregate by just summing those histograms. So these are the 4 steps. Doing this in a loop here. So recall that I'm just taking a file here and repeating it 4 times. So I have 4 paths here. So I'm going to do the read tree step, then I'm going to do the calculation, and then I'm going to create the histogram. I'm going to add those histograms to a list, which I'm then going to pass into the delayed sum. So I'll go ahead and execute these cells before I talk a little bit more. I'm going to do the same thing without Dask, so it can just run in the background, and we'll scroll back up. Okay, so as I was saying, we have our steps. The final result of after our loop here is just to have a list of delayed objects that I passed into the final aggregation function. And I'm going to go ahead and visualize this. So we have now our read tree step, the calculation, the histogram on each file, and finally combining everything in the final step. So this is obviously a small workflow here, but it's very representative of something that is quite common in Dask for folks that are just getting started and trying to scale up their specific workflow. Plugging into delayed is kind of a first step to take something that perhaps isn't just operating on arrays or just operating on data frames. It's a first step to plug into the Dask ecosystem, to just start delaying an existing workflow. So what I did here is I went ahead and timed this. So recall I had 4 files, and each file, when reading, I added that little sleep step to kind of fake it being a larger file. The total time to execute the full calculation was 1.18 seconds on my laptop. And even though with 4 files, we waited 1 second per file, I mean, this is a representation of Dask being parallelized. So Dask executed all of those read steps in parallel, each one, adding that additional unnecessary 1 second. So if we compare this to the serial, this is the exact same setup here, but this time without Dask, of course, it took over 4 seconds, because in this loop, each time we read the tree, it took that sleep of 1 second. So I wanted to show that just as an example of Dask executing things in parallel. So I'll take a second here to explain. There's kind of 2 there are 2 things that Dask is trying to improve. One is adding parallelization where it can, but second is out of memory computation. So if you have a workflow that at some point in its life cycle, perhaps you'd be taking up more memory than your laptop has. If you can chunk that computation you'll into smaller pieces using Dask, you'll be able to execute that computation without running out of memory. So those are the 2, especially in like a laptop setting. Those are 2 things that Dask really makes possible. Okay, so now we'll move on to the first of the kind of dedicated APIs. Of course, delayed has been the flexible parallelize or make lazy any workflow, but Dask.array is very targeted. Dask.array is meant to really recreate the NumPy array as task graph creation as a task graph creation API. So when you call, numpy.random.standard normal, you immediately are creating an array on, in memory. But when you call the Dask version of that, you are not creating any data. You're creating a small amount of data, but that data is just the Python dictionary, the task graph that will eventually call a NumPy function to create a set of standard normal functions, all however many chunks you've asked for. So we'll show this with a small example. So we'll import NumPy and Dask.array here. So here I'm calling just the NumPy ones function. So I'm creating an array of length 10, all ones. I can sum this, of course, 1 10 times is 10. But here's a representation of, two, excuse me, 2 chunks. So the first 5 and the second 5, of course, if we add these together, we still get 10. But here is that exact same, this sum of, of the array of 10 ones broken in half. Here it is in Dask terms. So we're asking, it's the exact same function, but Dask has this extra argument chunks. And this is saying, give me a Dask array that will eventually yield a NumPy array. But when chunking, go ahead and make each chunk of my array length 5. So here's the Dask array. As I was saying before, when you call the Dask version, it's not a new array library. It is where you're creating an array with some different representation. You've created a task graph that will eventually be an array. So the Dask version is really just instructions. And so another good thing about using Dask in Jupyter, some of these representations in the notebook are pretty nice. So you can really see what your array looks like. You can see information about the chunks, the structure. It's all very useful information. So of course, the exact same result we'll get by calling some of the Dask version, but we have to call compute to actually get it. Same thing. So the really nice thing about the kind of targeted collection libraries like Array and Data Frame is you can call most of the APIs. There are some things in NumPy and Pandas, some parts of those APIs that cannot be translated into task graph, into a task graph generating form. It just can't be kind of mapped to a lazily evaluated workflow. But most of the Pandas and NumPy APIs are recreated in Dask. And so one thing I'd like to show is chaining something together. So starting with the simplest case is just add. So adding a number to an array, of course, simple operation. But I also wanted to show that one thing that you can do with Dask is instead of calling .compute on a collection, you can pass multiple collections to Dask compute as a function instead of a method, and you'll get 2 results. But one of the things Dask will do is it will inspect both collections and it won't repeat work. So A3 is dependent on A2. And because we're passing in A2.sum and A3, Dask will only compute A2 once and then compute A2 sum and then A3. So it will, the repeated work is avoided in Dask world as much as possible. Something with a few more steps, a little bit more involved. We'll create a bigger array and take a look at it. So, this is another just array of ones now in two dimensions with some more chunks, a little bit bigger. And I can do whatever Dask allows. I can do to this array in kind of the NumPy world. So we'll take its transpose and add, do some NumPy slicing, take the mean along one axis. And so this is really building up a number of steps, and we'll see that here when we visualize it. So yeah, here's the task graph for that operation. Not that it has too much meaning, but really just to show that you can really just take the NumPy API, do what you would normally do with NumPy, but say this array was tens of gigabytes. it obviously wouldn't fit in memory in most folks' laptops, and you could still execute it with the exact same API. I'll take a second here to mention Dask optimizations. So I won't go too deep into this. Okay, it's more of a high-level overview, this tutorial. But one other nice thing about the dedicated collections APIs over something like delayed is because they're a little bit more targeted. There are some assumptions that can be made about some steps, and Dask can optimize these task graphs. So when we actually call compute, an optimized version of the graph is going to be computed by default. But when we visualize, we get to see the whole graph by default. So I just wanted to mention here that sometimes one could say, oh, yeah, I have this in delayed. Why, I don't need to worry about, trying, perhaps using one of the more targeted APIs. There is a benefit. Not only do you get to, reuse an existing API, but second, you get to take advantage of some optimizations that exist for array-specific and data frame-specific workflows that have been built into Dask, because Dask can make assumptions about what's happening in the task graph when it knows that we're operating on arrays. In the delayed case, it's very generic. It's like Dask doesn't make any assumptions about what's going on in a delayed workflow, because it's meant to be as flexible as possible, and so it won't be able to add in the optimizations of the graph. Okay, so from here we'll move on to a quick description of Dask data frame. Dask data frame I'm going to spend kind of the smallest time on today, mostly because I'd really be repeating myself quite a bit with what we were just discussing with Dask.array, because Dask.dataframe to pandas is Dask.array to NumPy. It's the same idea here, where we take a ubiquitous API. So many folks in the PyData ecosystem have touched pandas before, and so as with NumPy, and Dask.dataframe is meant to just recreate that API in a partitioned way. So it's on each partition of a Dask.dataframe, a pandas.dataframe will be computed, and all of this, all the functions and methods in the pandas world are available to you. Not all, most. So just a very quick example here that we can just take a look at is Dask has a datasets module for doing little tests, and so we can create just this example data frame that has 4 columns, and we can do a group by and grab group by the name, grab 2 of the columns, compute the mean of each of those. And before we compute it, we'll go ahead and visualize it. So you can see so this is quite the workflow. Doing the group by really forces the task graph to grow quite a bit. Same deal, we can just call compute and we get a result. So as I mentioned, I don't want to spend too much time on Dask data frame, because really the point here is to show that we have these APIs. I'm really driving this home. We have these APIs that are very popular, used all over the place, and Dask really just gives you the ability to scale them up. Okay, so the next thing I want to talk about is Dask, the distributed project. So far, everything that we've been doing today, and talking about delayed and Dask.array and Dask.dataframe, we've been using the default scheduler, the default execution engine, and that has been just the threads on our laptop. So this will parallelize computation on a laptop. For example, it'll allow you to do out-of-core computation on your laptop. So if you have a 50 gigabyte data frame, you can partition it to do operations on it without running out of memory. But the distributed engine uses this client plus cluster model, where the cluster has both a scheduler and any number of workers that the scheduler is communicating with, and telling them what work to do. So the best way to kind of get a first look at the distributed scheduler is to run it on your laptop. So you can create a local cluster with the distributed project. So I will go ahead and create both. I'll bring in the client and the cluster. I'll go ahead and create a cluster. Another useful thing in the Dask ecosystem here in a Jupyter Notebook is the representation of the cluster here. So you can see information. When I went ahead and created the default local cluster. So on my laptop, that gave me 5 workers. It's using all of my RAM. But of course, I haven't executed anything at this point. I haven't even connected a client to it. So I'll go ahead and do that. So now at this point, I have the complete graphic up here. I've created a client, or I created a cluster, then I connected a client to it. And so far, all very simply on my laptop. So at this point, I will go ahead and do something that unfortunately folks connected with are following along in Binder won't be able to add this part, but it's okay. The whole notebook will still be executable. So one really cool thing is the Dask, the dashboard. So when using distributed, you get access to a lot of diagnostics, and I'm going to pull up 2 specifically. I'm going to pull up the task stream, and I'm going to pull up a progress bar. I'll go ahead and give myself a little bit more room. Okay. So one of the I think targets for an audience like this is how can I have a cluster that's not just my laptop? And the ecosystem is very fruitful. We have a number of projects that allow users to kind of pull a cluster off the shelf. So there's the Dask Job Queue project, which provides clusters for common HPC systems. There's Dask Cloud Provider, which provides clusters for many of the cloud vendors. Dask Kubernetes. Dask Gateway is a project that allows like a system administrator to provide resources to folks. And there are more beyond this, but I don't want to go too deep into that right now. So I did write a small example here showing the same workflow that I had so far, where I used a local cluster. You could just substitute in HT Condor cluster if you have access to a Condor system. And I created that. I instructed it to use 2 GB of memory per job, then .scale to scale this up to 10 jobs. That would give me 10 workers, and then connect a client to it. And you can pass in a computation to the client, and boom, there you've just sent that task to the cluster. So this is really the power of distributed, the distributed project. So now that I have a local client running, I will compute the same thing that we did earlier with Dask.array. My zooming up here a little bit. The Z, it was this this multi-step calculation I did in the Dask.array with a Dask.array workflow. So now that I have a distributed client and I've got some of my dashboard utilities here, we can compute this again, and it was very fast. but the point I'm making here is distributed has a great set of diagnostics, and we'll do something that takes a little bit longer in a second. But you can go and you can actually see what happened in the task graph execution. And so you can really learn a lot about what may be bottlenecking your workflow or something by plugging into the diagnostics that distributed provides. Okay, so with that introduction to distributed, we'll move on to the final component of today's presentation, and that is adding to the Dask ecosystem here. So especially in the context of a high energy physics workshop. So we have been working, collaborating on for almost a year now on the Dask Awkward project, and we've also worked on the Dask histogram project in the past. And this is to bring native support for both awkward arrays and boost histogram objects to Dask. And so we'll showcase this with a small example. And I do want to note here that Dask Awkward is a ongoing project. It's usable. It's an alpha status right now because it's part of the awkward array, the next version of awkward array that's going to be released later this year, awkward version 2. So you'll notice that when I imported awkward here, I'm importing this v2 submodule. So with that said, we'll go ahead and work out a quick example, and this will be a small, pretty simple one. Like I mentioned, this is a bit of an appetizer for a couple of the follow-up presentations that are coming up. So we'll bring in our imports. So with Dask Awkward, what I'm doing here is I'm reading in a Parquet data set that's on some remote system. So I have a small, Higgs to muons data set stored in Parquet on S3. It's not super big, but I did want to show that this was the capability to access remote file system here. So if I look at the data set, this executed very fast. I have a Dask Awkward collection from a read Parquet function, and it has 50 partitions. So this data set here, wildcard had 50 files. So this is partitioned on each file. So, and then in executed terms, if I were to execute this, it would be reading 50 awkward arrays to make one final one. So what we are doing, what we've done a lot of and will continue to do as this project evolves, is exactly what's done with Dask.array to NumPy and Dask.dataframe to pandas. We are doing with Dask Awkward to awkward. We are trying to recreate the complete, as much as possible, the awkward API, but just Daskified, made such that all of these, the calls with the Dask Awkward version just create and grow task graphs. So the example I'll show here is I'll use the awkward API, but of course the Dask Awkward version, to apply some requirements on this data set and grab some value and make a histogram. So using the awkward num function, I want to grab pieces of this data set where there's at least exactly 2 muons. Once I've done that, I want to just calculate the minimum of the muons have a PT, a transverse momentum. So I also want to just grab, again, using the awkward names, using the awkward API, grab the smaller of the 2 transverse momentum values, and then I'm going to histogram that value. So here in the histogramming step, I'm passing in a Dask Awkward result as an argument into a Dask histogram function. So there's good interoperability going on here. These libraries know how to speak to each other. So I'll go ahead and execute these cells. Before I compute here, I'm also, I imported hist earlier. I'm going ahead and passing in the result of this computation to the hist library so we can take a look at it. So we'll go ahead and run this, and we'll see on the right, we're going to see Dask doing its thing. There we go. So you can see I had all 10 of my workers executing in parallel to get this final histogram. So you'll notice I explicitly passed in the optimized graph equals true here. So let's take a look at the difference. And the task stream is going to change quite a bit here. So if I don't optimize the graph, you'll notice there are a lot more things going on we had, I'll zoom in here a little bit. We had more steps happening. So you'll notice there was a get item call, an equal call, get the num call. So there are a lot of steps that happened to actually execute this result. But when optimized, there was just one step called histone block. And this, I'm going to kind of bring up again what I mentioned earlier about optimizations. What Dask was able to realize here was that all of these steps that, not all of them, but most of the steps could be executed really as one step. So I will visualize the task graph to show this. So first, this is a little bit of a big graph, but I'll use one partition as an example. We have the reading of the parquet. We're accessing the muons part of the data set. We're doing some operations with the num function, equal, doing the selection, another get item call, then calculating the min, then doing the histogram. And then finally, once we've done the histogram on one of those partitions, we start to aggregate them. So that's why you see this hist aggregate, and eventually we end up with the final histogram here at the very top. So that is the complete task graph. That's everything we've asked for. But Dask will go in and recognize that everything I showed here on the left, this can all be fused together. And one of the huge gains from that is every single time Dask computes a result and is going to reuse it, it may need to be communicated between workers. And when we can reduce the amount of communication between workers, that's overhead. And so Dask will optimize this graph and fuse many of those parts that all get sucked into one step, really. And so everything that was in that kind of long column basically was able to be combined into a single step here. And it just takes the name of that step, histone block. But the power of using a dedicated API, targeting a dedicated collection, targeting a specific API, is Dask is able to bring in these kind of optimizations. So this is just one more time I wanted to mention the delayed is very powerful in that you can turn any Python workflow into something that can be executed as a task graph with Dask. But there's really a lot to be gained from starting a project like Dask Awkward and Dask Histogram, where we can recreate these APIs and do things a little bit better than perhaps delayed would be able to do. So I've spoken to folks who've had the question, oh, like, why not just, delayed exists, why not stop there and just implement everything with delayed? It seems powerful enough. But there's really a lot to be gained from these dedicated libraries. Okay, so those are the examples that I wanted to show today. So then I just wanted to wrap up with a few minutes on some final thoughts here. So as I already mentioned before, the Dask universe is large now. The project has been around for quite some time. And so we've really just scratched the surface of what one can do with Dask. But hopefully this was, hopefully you gained something from this if you hadn't seen any Dask before. And if you have, hopefully you saw a little bit more. There are a lot of resources available. The official Dask documentation is quite large. And there's also a longer tutorial. Of course, this is about 45 minutes. But there is the official Dask tutorial is meant for 3 to 4 hour setting. The kind of final call to action here that I wanted to mention is that the Dask Awkward project specifically definitely welcomes folks that are willing to live on the edge a bit. And please stay tuned for some follow-up presentations that, like I mentioned, will showcase more connections between the Dask world and Scikit-HEP. yeah, going back one more time to this call to action for people to use Dask Awkward. Like I mentioned, it's in development. We're working in parallel with the work on Awkward version 2. So if perhaps you're using Awkward and you're getting ready to transition to being able to use Awkward version 2, for example, and you see yourself as perhaps having some value in adding Dask to your stack, please give this a shot. We have a lot of the API implemented, but in kind of the Dask world, a lot of things come into the libraries on a user feedback basis. So folks will come across a function or a method in NumPy or Pandas that they need for their Dask workflow, and perhaps it hasn't been added yet. And it's very common for people to come to the Dask community and say, hey, I'd like this. I'd like, obviously numpy.transpose is implemented, but say numpy.transpose wasn't implemented. You come across that, you can just go to the community and say, hey, can we get numpy transpose added as Dask transpose? And usually there's someone, if it's possible, there's someone around that's willing to add that. And that same pattern we expect to adopt in Dask Awkward. If there's corners of the API that don't work in the Dask workflow, we'd be happy to work with anybody that needs that. So that's everything I had for today. Looks like we have a good bit of time for some questions. And yeah, thanks for your attention.
Thank you so much, Doug. That was very clear, and I think you explained everything nicely, but also got to some really quite interesting examples in that last section there. So we do certainly have time for questions, and just a reminder to people that you can ask more of them if you go along to Slido. Let's start with the first one that was asked by Michael, which you asked, can Dask optimize or automatically determine the chunk size? Could I ask Dask to ensure that chunks are no more than half my available memory?
Yes, there are some Dask configuration options. So there's a blog post even that goes into, I can actually go to, while I'm sharing my screen, blog.dask.org. Yeah, choosing good chunk sizes in Dask. This is blog.dask.org. There's a paradigm around chunking. So I'll mention, yes, Dask will try to automatically do things, but it is worth spending a little bit of time thinking about this. There's, like I mentioned, there's configuration options, and then Dask will, depending on the size of your data, how you've partitioned it, there are some automatic things, but in general, it's good to think about this and test, actually, like create some small test cases and see if your chunk sizes are a problem, for example. Yeah, I hope that answers the question.
Oh yeah, that's a really good resource for answering that question. Clearly, you can dig into a lot of detail there. Let's just also deal with Michael's second question, because I think it was answered in the presentation. He asked if Dask delayed was implicitly parallel. I didn't notice any declaration of thread resources. Right,
yeah, so I would say the execution engine is explicitly parallel. So whatever task graph gets created by a delayed workflow. So I'll go back to this example that I showed. So this graph was created with delayed. The delayed itself doesn't necessarily know to create something that is parallel, but the task graph, its structure, this structure is obviously parallel. This calculation, for example, I'll drag it over here, is completely independent of this read tree. So obviously this calculation is dependent on this read tree. So the execution engine will go in and see that I can execute read tree calculation over here on the left-hand side at the same time that I can execute read tree over here. So it's not necessarily that delayed knows anything about parallelization. It's once you've completely constructed your task graph from delayed operations that the execution engine will go, oh, hey, look, this doesn't have any dependencies. I can execute it at the same time with this other thing that has, different dependencies or something like that.
Okay, that's great. Thanks very much. Let's switch it up. Let's go to Doug's question. I guess you're going to ask a question live, Doug.
Yep.
You go ahead.
Yeah. As I'm a resource provider, so one of the things that using a Condor queue, there's obviously scheduling time for to spin things up.
Mm-hmm.
Are there settings so that multiple workers can flow into the remote object, the remote, job slot?
There is an
and just keep using it, and then eventually, shut down at a time limit.
Yes, there are features in the cluster in the cluster library to adapt. Yeah, there's a scaling and adapting kind of a max and min capabilities. Yeah, those I don't have any personal experience with at this point, but I know that there's functionality there.
Right. Thanks, Doug, both of you. Okay. Nice question. Let's go to the next question. So Eduardo was asking a bit more about the future of the Dask and PyHEP collaboration. So if you're going to get any insight into what's on the horizon and how people could engage even more in that, because that's obviously something that's very interesting for our community.
Right. Yeah. I'd say, like I mentioned before, stay tuned. There's a couple more talks coming up, but I will just kind of give a little bit of a spoiler. One of obviously the talk description is there, the abstract for the next two, so you can, not really a spoiler, but we're gonna hear a little bit about connections between Dask and uproot. So reading root files directly into Dask collections. And I purposely skipped over that a little bit by using a Parquet data set. And secondly, we'll hear about some being able to access remote file systems. And that's a big thing in Dask. I mean, a lot of, I'd say the majority of people that use Dask heavily are using some, for example, the Pangeo community has large data sets, obviously not stored on local systems, stored somewhere in the cloud, and so it's a big thing in the Dask world to be able to access the Google Cloud, AWS, whatever, some remote stuff. So connecting xrootd with the kind of platform that exists in the Dask universe called FSSpec, connecting those together is something else we'll hear about. And obviously, I mean, Dask awkward is relatively young in the scale of the, Dask has been around for since about 2015, if I remember correctly. And, we started working on Dask awkward last year. So we'll be working on Dask awkward for a little while longer. We also have another project that we're collaborating with awkward folks on for better pandas support and awkward. So the train is moving, and there's more to do.
That's great. Sounds like quite an exciting time to be involved in that and keeping an eye on it. Okay, grand. Let's go to the next question, which is, how do the cluster workers communicate with the main node, and do you need a shared file system to make this work?
So you don't need a shared file system. There are a few communication protocols. Unfortunately, I don't know the nitty-gritty details, but serialization matters a lot here. So in Python world, the objects are serialized and then sent over the wire, so that, but Dask does try to do this as well as it possibly. This is one of the, I'm not super involved in the distributed project. But having spoken with some of those folks, it's always it's a pain point that they are very aware of, always thinking about. And Dask does try to limit the amount of communication that has to happen over the wire, and limit passing big objects, for example. But that really how the clusters communicate, the components of the clusters communicate by serializing objects, be that data or functions, and passing it over the wire.
Okay, great. Thanks.
Shared memory, though, is something that's being explored. It's been explored in the past, but it's being explored again by one of my colleagues. And there's actually likely, I'm going to plug, there will likely be a presentation later this year at PyData Global on trying to use shared memory in Dask.
Okay, that sounds very cool indeed. All right. Then let's go to the next question, which is just, I think, a sort of reprisal of what you were saying. To summarize, is it fair to say that the reason to use Dask data frames, array, etc., is just that compared with delayed, they have further optimizations?
That is certainly a main component of the argument, I would say. But then secondly, you'd be recreating the wheel in a lot of cases. A lot of work has gone into being able to kind of drop in replacement, the import. So I wanted to highlight the optimization because I think it's a cool thing to see. It's nice to see that real benefit. But even beyond like runtime efficiency, the recreating data frame group by with delayed, I can't even think right now, right? Like it'd be a project. So there's obviously a huge benefit as well to having that existing API in terms of just being able to produce code quickly, get things moving.
Right. Well, indeed, of course, that's one of the reasons that we like Python so much, is it makes people efficient as well.
Yeah.
So we care about that a lot. Okay, that's very good. And then there was another question just about the list S expression, but I think that was pretty much answered by Jim, actually, that it was just a way of representing the graph in this particular case, unless you have any more insight into that.
No more insight. I like to point out that it's like an S expression because before I ever used Dask, I had played with Lisp. And so when I saw that comparison, it really clicked for me. So for anybody else that perhaps had that experience, I wanted to just point out the connection between S expressions and a delayed function call in Python.
Very nice. Thanks very much. Okay.